So, getting started with Akka Streams. That's my intro. I'm not a comedian. I don't have like well practiced. Right. So first, who am I? I'm Paul Kinsky. I'm a platform engineer at Nitro. We work on making documents smarter, PDFs slightly less awful to deal with. Great company, but we didn't pay the expense report for the pizza, so I'll keep going. Right. So streams. That's what this talk is about. Why should you care? They're everywhere. You've got real-time streams of data. You've got stuff like streams of log data, streams of data from Internet of Things devices, sensors, streams of data from your machines. You have real-time, just big data. Anything that is too big to fit in memory is necessarily processed as a stream, right? You have a stream of chunks that you process one after another. And of course, you have streaming media, just bulk transfer of data. You have like Netflix, your Spotify, et cetera. That's multiple billion-dollar companies that just like stream data. So it's everywhere. TCP is streaming data. Like React, that new hot JavaScript framework, it works with streams under the hood. Streams are everywhere. All right, so they're sort of, what are streams, right? Two types of streams that people really use, distributed and local. First, distributed, they're really cool. It's not what this talk is about. You have Spark, you have Storm, training models based on real-time streams of data, and then just, of course, big data. So, and then local streams, right? Where you want to have more granular control. So say you have complex logic, right? The first one's sort of based on something we're running in production, or going to be running in production soon. But say you have like a really granular flow of data, you want to pull messages down, use them to fetch things from S3, do something to that thing you just fetched from S3, upload it, create an event. You can't really do that on Spark, so you need to control how data flows at like sort of a more granular level. Or, again, granularity of control, right? So I just said TCP is streams. So instead of when you get a request to your framework, taking the whole thing into memory and then processing it, you can get the header and the rest of the request as a stream, throw away that stream and not consume it if the header's malformed. So that would be really helpful, say, if you're getting DDoS. And of course, building distributed systems, right? So you have your Sparks, your Storms. You can't just like put the spec for that on top of an x86 chip and expect it to run. Someone needs to build those, and stream processing systems are a great way to build those. So, all right, here's the traditional stream model, right? You have a publisher, you have a subscriber, you send data from the publisher to the subscriber. There's some choices with that. You can either push or pull data. This should be pretty familiar terms, right? Push, the publisher controls this, or initiates the transfer of data. So that what happens is data shows up at the publisher, it sends it to the subscriber as quickly as it shows up. Subscriber just has to handle whatever data is sent down the stream, and with pull, that's like the opposite. The subscriber controls the flow of data, initiates the flow of data. So you have like, say, polling, basically. The publisher would go, hey, or the subscriber would go to the publisher and say, hey, give me data. Publisher would send it downstream, et cetera. And that's if the publisher doesn't have any data, it doesn't have anything to send downstream, it gives an empty response. So you've got a sort of trade-off, like 2x2 square here, right? If you're pushing, the subscriber is faster, that means you can just publish as much as you want downstream as fast as you want, and the subscriber will always be able to handle it because it can consume data faster than the publisher can produce it. But then the publisher is the producer is faster, you're going to get a buffer overflow, or you're going to have to drop data, right? Buffers are bounded. We're working with machines. They have finite memory space, so you can't just buffer data forever. If the publisher is consistently faster than the subscriber, you have to drop data, or you're just going to crash. On the other hand, pulling, right? You're pulling from upstream. If the subscriber is faster, that means you're just going to get network congestion, right? You're going to be pulling for data repeatedly. It's not going to have anything. You're going to have your server fall over. Then, of course, if the producer is faster, there's always data when you go upstream to get some. All right, so reactive streams, right? This is the standard on which Akka Streams is built. It's not the only thing using it. Reactive Streams uses it, a few other initiatives. Engineers from like Twitter, Netflix, TypeSafe were all involved in creating the standard. So the whole idea is that you have bidirectional flows of data. Downstream, data gets sent downstream, and then demand is sent upstream, right? So the upstream sends data, or the publisher sends data to the subscriber when and only when there's outstanding demand, right? And the subscriber signals demand upstream. These two aren't necessarily coupled. So you could have data or demand sent upstream by the subscriber, then 10 minutes later, the publisher has something to send, it can fulfill that demand. So it's sort of decoupled, it's very message driven, it's entirely just based on messages sent between publishers and subscribers. So let's look at how that works when the same subscriber is faster, publisher is faster. So subscribers faster, the publisher always has surplus demand to fulfill. That means that it can always just send stuff downstream. It's essentially the push model if the subscriber can handle it. If the subscriber can't handle it, if the subscriber's slower than the publisher, that means there's no outstanding demand most of the time. So therefore, when the subscriber sends demand upstream, the publisher will basically immediately fulfill it. That's essentially the pull model because you have data being sent downstream in response to demand being sent upstream, right? So that's it. So essentially, it's switching dynamically between push and pull based on the relative speeds of the subscriber and the publisher, which is really great because it's basically back pressure. That's another term for it. So if you're dealing with flows of data where the relative speed of different components changes, you'll on the fly switch between pulling and pushing on each publisher-subscriber connection, which is pretty nice. But onto the example problem, right? That's the introduction. So transaction log. Let's say this is stolen from the second chapter of the book I'm working on, Akka Streams in Action. The idea is, say you work for a bank, there's a disaster, middle of the night, you get woken up, you've lost all your account balances, right? Everything's doomed, but ray of hope, you have the transaction log. So you have to build a program that can run through the transaction logs, incrementally consume them, and use them to construct the account balances. So what would that look like, right? For convenience and because CSVs are everywhere, it's a CSV file, you have your header, type, name, and amount, your data, it's either a deposit or a withdrawal, and then the name of the account and the amount in dollars, right? Super simple version of the problem, more as just to illustrate some concepts. So let's start by building a source that we can use to get the data, the lines from the CSV file, right? So sources, there's source of data, right? But it's one of three entities in Akka Streams that you'll be using most often. Sources, flows, and sinks. Sources produce data, flows transform data, sinks consume data. But the key concept is that they're not actually describing running stream pipelines. They're blueprints that you can combine with other blueprints that you can create. You can do so across threads. You can materialize them to create running stream pipelines multiple times. They're thread safe, they're immutable, they're typed, they're all that good stuff. Running streams, not so much, but fortunately we don't have to deal with those until runtime. So our source. So we're working with just some Scala utilities because it turns out it's actually a non-trivial problem to take chunks of bytes and split them on new lines. Because what if you need to create lines that are across multiple chunks of bytes? You need to create a stateful stage. You can do that in Akka Streams. It's more code than I want to introduce right now. So we're just using the iterator of string from just one of the main Scala packages. So what we do here, we create a function that creates our iterator. And we create a source. And remember, sources are describing the pipeline. They're not a running pipeline. So what it needs to do, it can't take the iterator directly because iterators are mutable. You can only use them once. It takes a function that creates the iterator. So you can think of the source as sort of a composable factory, right, for a part of a stream. But factory is a dirty word. Don't forget I said that. So here we have a source of lines. It's just wrapping an iterator. And we can use run for each. What that does is append a sync that runs for each element some function. We're just passing in print line. And you can see here if we run it on lines on our CSV file, you get type, name, amount, deposit, withdraw, et cetera, the lines that I just showed you. So that's OK, right? We've done the first step. We've got it to the point where we can work with it. So we need to actually parse each of those lines. It's a comma-separated value file, comma-delimited lines, right? So what we do is we map over each, we split it based on commas, turn it into a list. Now, this is actually a flow, right? We're describing a transformation pipeline here. So we already have a source of data. We want to create a pipeline that we can bolt onto it that runs our transformations. So what this is, it's starting with sort of the identity flow. That's what a flow.apply with a single type parameter gets you. Just a flow of string to string that applies no transformations, just passes things through. Then on top of that, we're mapping, we're splitting each. And so you can see here, if we run that with run for each again, you get a list of type, name, amount, deposit John Doe 100, withdraw John Doe 50. So that's more parsed, right? This is sort of another step along getting it to work. So now you can see we have sort of a mix of header and data. So another thing taken right from the Scala collections framework, drop, right? So we create another flow pipeline that does the same thing, but first it drops the first line. Again, we append that pipeline to the source of lines, run it for each by appending a sink, and then we just get lists of data. So now that's, we don't want to work with that, right? It's strings, it's lists, we want case classes. So we're going to do something like this. We have transactions. Transactions either a deposit or a withdrawal. You have an account and amount, and et cetera. Just a normal case class. So what we're doing here, we're using collect, again, from the Scala collections framework. Well, the same concept at least. And we're matching on either a list with the first element being deposit, and then an account and amount, turning the amount to int, or withdraw in the same things. Now you should note that if an exception is thrown here, when you do toInt, it will fall over. You could make a better unapply function for deposit and withdraw that actually parse those lists or directly parse CSV lines, but outside the scope of this talk. So when you run lines through rows, through parsed, and then append the for each sink to it that prints each line, you get a deposit object, a withdrawal object again, right? As expected. All right. So then let's build a sink that will apply the transactions. First, we need to know how to apply a single transaction. We're basically going to be folding over a stream of them. So you have a state, you have a transaction. If it's a deposit, you update the state, which is just, a map of string to integer, map of account name to balance. And this is just basic map manipulation. And then you just create a sink that folds over it. So what this does is it starts with that initial state, that empty map. For each transaction, it applies it with a apply transaction. And then when it eventually finishes, when the upstream stream completes, there's a future that's yielded when you run this that then completes with the final map. So you can see here we create a parse and apply. That's a sink. So what we're doing there is we're prepending the rows and parse flow to apply transactions. We're using toMat here to keep only the right materialized value. That's the map of string to integer. That's our final account balances. So you create a pipeline that's a fully connected stream processing graph, again using toMat, and that every inlet and outlet in that is fully connected, right? There are no sinks that have empty inlets. There are no sources that have empty outlets. So this can be run. So you do that. That gets us our future. We await it. You get a map of John Doe to 50 because if you remember, we deposited $100, withdrew $50. That's trivial but correct. So far this is pretty boring, right? You could use the collections framework to do exactly the same thing. It's like a list of two things that we're running something over, parsing, et cetera. So let's work with a million-line CSV file instead, right? So here we're creating a source by concatenating a header row, and then just a deposit by Jane Doe for $1 a million times. So we create our pipeline, we run that, and as expected, you get a million things. Now's a good time. Does anyone have any questions?
What does the keep write do again?
All right, so every source, sink, and flow has a materialization type, right? The materialization type is something that you get on the side once when you create it. So if you're, say, creating a source from bytes from a socket, you might get like a closable from that at materialization time that would let you close the socket. In this case, with our fold sink, we're getting a future of the value it creates by folding as our materialization type. And toMat, instead of it allows you to pass in a function that just takes the left and right materialization types and chooses which one to keep. Keep.right is just a function that takes the rightmost of those two types. Anyone else? Right. Right. Keep.left is just a shorthand for keeping the leftmost element of a two-element tuple. Oh, sorry. Right. So let's look at some actual types here for a second. So let's look at the sink that we created, parse and apply. That's tiny. Right, so. Actually, it would be better to do this in the REPL. Right, so this is the type of the sync. You can see it's a sync with two type parameters, string and a future of map of string to int. So that's the materialization type. That's the future is something that you get when you materialize this sync, because it's consuming a bunch of transactions, applying them to some initially empty map, and eventually completing the associated promise with that future to return the eventual result when it completes. So that's included in the type parameter. And so let's say, take a look at lines, right? That's the source of lines. So that has a materialization type unit. And when we're combining something with materialization type future of something and one with materialization type unit, we need to choose whether to keep one, none, or both of those materialization types. And keep.right is saying keep the rightmost of those materialization types. When we're appending a sync to a source, the sync is on the right, the source is on the left, because left to right, right? So keep.right is just saying keep the future of map of string to int and not the unit. There's also keep.both, keep.left, keep.neither. Does that answer your question? Right. So, so we created a pipeline, right? Something that we can use to complete like the semi-trivial task of parsing a CSV file, incrementally consuming it, and running something across each element, each row. And shown it does work with a million-line CSV file. I can do this in the REPL if you want to, but I've found that it's wise not to tempt the demo gods. Right, so we've created our pipeline. Let's see if we can do something completely different with the same pipeline. Say, take a WebSocket, push messages describing transactions up that WebSocket, and get the current state back. So we need to change a few things to do that. First, we need to go from messages to strings and back. So what we're doing, we're using Akka HTTP and collect again, because WebSockets support both binary and text messages. So we're only taking the text messages, grabbing those, piping them through all rows, because this time we don't have a header row. We're just using CSV over WebSocket because we do crazy stuff like that. Parsing it again. And here we're using scan, right, instead of fold. What scan does, almost like fold, but instead of just emitting the last element, it emits every element. So every update to the state will be emitted, sent downstream. So what we're doing with that, then, is we're using those states to create new text messages. And this is being sent via the WebSocket. So let's check that out. The surrounding code is also in here. So you have a really simple DSL that I'll be skipping describing. So you just have any get with no path will just serve up this resource, this HTML page that is the front end. Anything to WS will handle every WebSocket message with this flow, parse and apply WS. So apparently the tooltips are not zoomed in on. That's just the flow that I showed in the PowerPoint. And then we're just binding to localhost port 9000. So I've got this running in the background, and the UI leaves much to be desired. It's using the console for logging everything sent by the WebSocket, because I'm a backend engineer, and that is how I consider UI. Right. So let's have, again, Jane Doe deposit $1. So you can see the resulting state is sent back down the WebSocket. So just keep doing that. It increments, take someone else. Give them $1,000, why not? And take $3,000 or take a few $1,000s. So this is not what you'd use for your bank, right? You can get negative account balances really easily. It's just to show how you can work with streams of data. Right, and you can do more complex things with WebSockets. You could very easily integrate something that works with futures. Like if you have, say, if you currently use futures for interactions with your NoSQL store, with your database, there's a map async that takes a function from A to future of B instead of A to B. You can like specify parallelism. You can do map async unordered if you want to remove the ordering guarantee in exchange for higher performance if you get an occasional slow element. There are just a ton of combinators that you can use, more so even than in the Scala collections library maybe, to transform streams, or transform specifically sources and flows. Then you can also create much more complex things using the graph DSL, which is outside the scope of this talk. So say you can merge multiple streams together. You can broadcast one stream to multiple consumers. You can balance one stream among multiple consumers if you want to add parallelism. There's a lot of stuff you can do. Right. And you can use Kafka, for example. There are existing libraries you can use to stream to and from Kafka, to Postgres, et cetera. Right. So contact info, Nitro careers email, my GitHub. Does anyone have any other questions? Cool. All right.
Maybe I just did the slide stuff, but it seemed like map were essentially the same thing.
Oh, sorry, I should have explained that in more detail. Right, the question was, it seems like map and collect are the same. They almost are. Map takes a function, collect takes a partial function. So what collect does, if the partial function is not defined, it drops the element. So if we were to send like an empty lineup or WebSocket, for example, collect would see that there's like an empty list after you split that on commas, and that would just be dropped. Whereas if we use map with a partial function, any element that was malformed would cause it just to fall over with a match exception. All right, I think that's all the questions. Yeah.